for most of human history. The ocean felt endless, unmapped, unclaimed, unbeatable, and for centuries one creature ruled the deep without question. The sperm whale, 60 feet long, 40 tons of muscle and bone, a head so massive it makes up nearly a third of its entire body. To early sailors, they were monsters. To whalers, they were floating treasure. To the ocean, they were ancient kings. And for millions of years, nothing hunted them efficiently, until humans arrived. When orcas attacked sperm whales, the whales relied on a formation that evolution had perfected over millions of years. A defensive strategy so effective it was almost invincible. They called it the Marguerite Formation. When danger approached, the pod would compress into a tight circle. The young and vulnerable calves were pushed into the center, while adults formed a living wall around them. Every massive head faced outward. Every tail pointed inward, ready to strike. To an orca, this was a nightmare. Any attempt to isolate a calf meant being rammed, bitten, or crushed by several 40-ton adults at once. For generations, orcas learned to give up. The formation worked, till it didn't. Because orcas weren't the predators that broke this system. Humans were. When 19th-century whaling ships entered the North Pacific, sailors quickly noticed something strange. Unlike other whales that fled immediately, sperm whales did the opposite. They stopped, they gathered, they formed circles. What evolution had designed as protection became a trap. Harpoon ships didn't need speed. They didn't need precision. The whales had already done the work for them. Packed tightly together near the surface, unable to dive or scatter, sperm whales were slaughtered in numbers never seen before. Entire pods were wiped out in hours, and for decades the kill rate only climbed. Then, something happened that stunned historians. Between 1848 and 1852, the sperm whale hunt rate in the North Pacific collapsed by nearly 60%. Not because humans stopped hunting, not because ships vanished, but because the whales did. Sperm whales began abandoning the Marguerite Formation. They stopped grouping near ships. They stopped surfacing together. Instead, they fled fast. They used powerful ocean currents like highways, slipping away before ships could close in. They changed their migration routes. They altered their surfacing behavior. And here, as the part that should be possible, pods that had never even encountered a whaling ship behaved the same way. Whales thousands of miles apart adopted identical escape strategies. This wasn't instinct, this was learning. And it was learning at a speed that evolution alone could never explain. So how did a species with no tools, no fire, and no written language abandon millions of years of hardwired behavior in just a few decades? The answer begins inside the largest biological weapon ever built: sound. Out of the 60 feet that make up a sperm whale, nearly 20 feet is just its head. Inside that head sits the spermaceti organ, a waxy, oil-filled structure that early whalers misunderstood so badly they named the animal after it. For centuries, humans harvested this substance for lamps, lubricants, and machinery. But today, we know what it really is: a sound engine. When a sperm whale clicks, air is forced through a pair of muscular lips near the front of its skull. That sound travels backward through the spermaceti organ, reflects off internal air sacs, then blasts forward again through a second wax-filled chamber. The result is a focused beam of sound, not noise. A weaponized sonar pulse, measured at over 230 decibels. Sperm whale clicks are the loudest biological sounds ever recorded on Earth. Louder than a jet engine. Louder than an explosion. Powerful enough to rupture eardrums, disorient prey, and possibly even stun targets at close range. But sound isn't just power, it's precision. Sperm whales hunt in total darkness, thousands of feet below the surface, where sunlight has never reached. Down there, vision is useless. So they see with sound. The hunt begins with slow, spaced clicks, like long-range sonar pulses scanning the water ahead. If a giant squid is detected, the clicks accelerate faster, sharper. They enter a phase scientists call a creak, up to 90 clicks per second. The whale is locking on. In the final moments, the clicks turn into rapid buzzes, tracking every twitch of the prey as the whale closes in for the kill. But hunting is only half the story. Because sperm whales don't just click at prey, they click at each other. These patterns are called codos. Short, rhythmic sequences of clicks exchanged during social interaction. At first, scientists thought codas were simple signals, maybe 20 or 30 total. They were wrong. In one long-term study in the Caribbean, researchers analyzed over 9,000 coda recordings from a single whale clan. They identified at least 21 core patterns, but with more than 300 variations in rhythm, spacing, and timing. They called it a phonetic alphabet. Not language as humans use it, but structured, learned, and shared. Calves spend years babbling before mastering their clan's specific dialect. They don't inherit these patterns genetically. They learn them. Different clans have different accents. When unfamiliar groups meet, they sometimes exchange no codas at all, as if they don't speak the same language. And each whale's clicks carry tiny, consistent differences micropatterns that remain stable over time. Researchers suspect these may function like names, an individual identity encoded in sound. Which brings us back to the whaling ships. If sperm whales can transmit identity, group membership, and learned patterns, then what else can they transmit? Warnings, strategies, survival information. When the Marguerite Formation failed, whales didn't wait generations for evolution to correct it. They shared knowledge. Somehow, and that knowledge spread faster than ships could sail. This wasn't just adaptation. It was cultural transmission. The first known case of non-human animals changing their global behavior in response to a human threat. And it gets even stranger. In 2016, a massive earthquake struck off the coast of New Zealand. Underwater landslides wiped out deep-sea ecosystems that sperm whales depended on for food. Researchers tracking the whales noticed immediate changes. Whales spent more time at the surface between dives. They altered their hunting depths. They abandoned old feeding grounds. They were responding to an environmental catastrophe together, not as individuals, but as a network. Some scientists believe urgent codas may act like alarms. Others think whales use shifts in tempo to convey stress or danger. We don't know the exact messages, but we know the outcome. They adapt, they share, they remember. And that raises a terrifying possibility. If whales can pass down survival strategies across oceans, what else have they learned? Because humans stopped hunting sperm whales long ago. But the soundscape of the ocean has only gotten louder. Naval sonar, seismic surveys, shipping lanes. The ocean is now filled with artificial noise that interferes with the very systems sperm whales rely on to survive. And if sound once saved them, sound might now be killing them. In Part 2, we'll go deeper into how sonar affects whale brains, why mass strandings happen, and whether humans are accidentally waging a silent war, using the same weapon whales depend on. The whales learned once, and they may be learning again. Make sure you subscribe so you don't miss it. By the time humans stopped hunting sperm whales, the ocean had already changed forever. Harpoons were gone, their explosive tips retired. Whaling ships were turned into museums, but something far more dangerous replaced them. Sound. Unlike light, sound doesn't fade gently underwater. It travels faster, farther, and harder. And over the last century, the ocean became loud. Very loud. Cargo ships alone now generate a constant low-frequency hum that blankets entire ocean basins. Seismic air guns, used for oil and gas exploration, release earth-shattering blasts every 10 seconds. Each one is louder than a nuclear explosion when measured at the source. Then there's military sonar. Naval systems emit focused pulses specifically designed to penetrate deep water the same depths sperm whales live in, and the same frequencies they evolved to use. And that's where the problem begins. Because a sperm whale's brain is built around sound. Their entire world is sound. It's how they navigate, how they hunt, how they socialize, how they remember. So when their soundscape breaks, they break with it. Scientists first noticed something was terribly wrong in the late 20th century. Whales were stranding themselves. It's not slowly or weakly, but violently. Healthy whales, with full fat reserves and no visible injuries, were beaching themselves en masse. Dozens at a time, sometimes hundreds. Autopsies revealed something deeply disturbing: hemorrhaging around the brain, gas bubbles in their tissues, and severe inner ear trauma. In some cases, the damage looked eerily similar to decompression sickness, the bends. But whales don't get the bends. They evolved to dive deep. Or so we thought. Here's what researchers now believe happens. When exposed to intense sonar, especially mid-frequency naval sonar, the whales panic. Their sonar-based perception collapses. Their auditory world becomes nothing but blinding noise. Imagine navigating a city blindfolded while explosions go off inside your head. The whale bolts. It ascends too fast, too shallow, too quickly. Nitrogen bubbles form in their bloodstream. Blood vessels rupture and their brains bleed. The whale strands itself, confused, injured, and unable to return to the deep water where it belongs. This isn't just speculation. In the year 2000, a U.S. Navy sonar exercise directly coincided with a mass stranding of beaked whales in the Bahamas. Post-mortem examinations confirmed acoustic trauma. The Navy eventually acknowledged the link. Sperm whales weren't spared, either. They don't strand as easily as beaked whales because they're larger, stronger, and more resilient. But they absorb sound differently. Their massive heads act like giant acoustic lenses, focusing sound inward. This means intense sonar doesn't just disorient them, it can physically overload them. Some scientists suspect that extremely close-range sonar exposure could cause direct neurological damage or even physical injury through resonance. The terrifying part: we still don't fully know the limits. We can't ethically experiment on whales, so we learn by watching them suffer. And yet, the whales adapt. Again, in regions with heavy shipping noise, sperm whales are changing their clicking patterns. They click louder, longer, more aggressively. But louder clicks cost precious energy they need to hunt. Other whales have been observed shifting their frequencies upward to avoid the low-frequency drone of ships. But higher frequencies don't travel as far, which means smaller hunting ranges, less food, and slower growth. The calves suffer the most. In noisy environments, the communication between a mother and her calf weakens. Calves miss cues, they stray too far, they fail to coordinate their dives. Some never survive their first year. And yet, the whales keep communicating. They don't go silent, they improvise. They adapt their codes, the Morse code-like click patterns they use to talk. They shorten them, stretch them, and change the rhythm, almost like someone shouting to be heard in a crowded room. Which brings us back to the question we still can't fully answer. What exactly are they saying? We know their codes carry meaning. We know they encode identity, that they're learned, not just instinctual. But could they also carry warnings? If whales once transmitted information about human hunters and their harpoon ships, it's entirely possible they're now transmitting information about sound, about danger zones, about shipping lanes, about the places where whales go and never come back. If that's true, then these whales are doing something extraordinary. They're mapping the human threat in real time, and they're passing that knowledge on. This idea gained serious traction after long-term studies showed that certain whale clans actively avoid regions with intense naval activity, even when those areas are rich with food. Other clans, unfamiliar with the danger, enter these same zones and suffer much higher mortality rates. This suggests that experience matters. Memory matters, culture matters, and sound is the medium for all of it. This realization has sparked something unprecedented. What if we could listen back? Not just record the whales, but actually decode them. That's where artificial intelligence is entering the ocean. Projects like SETI, the Cetacean Translation Initiative, are using machine learning to analyze millions of whale clicks. The goal isn't to create a whale-to-English dictionary. It's to identify structure, patterns, and context. To ask a simple question: when whales click differently, does something specific change in their environment? Is it food? Is it a threat? Is it stress? The early results are promising. AI systems can already cluster codas by social group. They can detect emotional shifts in vocalizations. They can even identify individual whales based on their unique click signatures, alone, something a human ear could never do. And here's the unsettling part. Some of the most distinct changes in whale vocal behavior occur right after sonar exposure. Clicks become erratic. Codas shorten. Social exchanges drop off. It looks, for all the world, like trauma. This raises an uncomfortable thought. If whales learn to outsmart 19th-century hunters, what happens if they learn to fear modern humans? What happens when an intelligent species starts to associate us not with harpoons, but with invisible, agonizing pain? Whales don't understand geopolitics. They don't know what sonar is. They only know cause and effect. Noise equals danger, and danger equals avoidance. This could permanently reshape migration routes, alter entire ecosystems, and silently erase whales from regions they once dominated, all without a single harpoon ever being fired. The ocean wouldn't look empty, it would just sound empty. And we'd be the only ones who didn't notice. But there's one final twist. Sound isn't only how we harm whales. It might just be how we save them. Some shipping companies are experimenting with quieter propeller designs. Navies are adjusting their sonar protocols when they're near known whale habitats. And researchers are testing acoustic sanctuaries, protected zones of enforced quiet. The early results show that whales are returning to these areas. They're clicking normally again, reforming their social bonds. The ocean responds when we finally stop shouting, which brings us full circle. Sperm whales survived extinction-level hunting by learning, by communicating, by changing faster than evolution ever could. They adapted to us once. Now the question is whether we can adapt to them. Because for the first time in our shared history, survival may depend not on who is stronger, but on who is willing to listen. Thanks for watching. If you found this story as powerful as I did, please like this video and subscribe for more deep dives into our incredible planet.